Hello, TIC, BC Part 1. This is Miss Yam, and it is Thursday. I want to thank you for your patience this week. I was hit really badly and was very, very sick. And I realize now as I look at my schedule for tomorrow, I won't see our class tomorrow, Friday. So I want to wish you all a good spring break. There will be spring break homework, and part of it is this screencast right here, and the rest of it I will make sure that it is all up and posted by the end of the day tomorrow, Friday. Okay? The first part of this screencast is going to be showing you the shortcut for implicit differentiation. I heard from a couple of you when Mr. Logue covered, and I think he may have not realized that we hadn't done the shortcut yet, and so he just used Y. So I'm going to show you here what the shortcut entails, and you'll see here the first thing I did was I wrote out a relationship between x and y that does not describe y as a function of x, and I went along and found dy dx the way that we've done it together, right, by substituting y equals f of x, and then working through with the chain rule, working through the product rule here where it was needed. And then, of course, we went and subbed back in f of x for y and f prime of x is for dy dx, collected like terms, and then finished with dy dx. With the shortcut, here's what's going to happen. The shortcut is going to allow you to go from the given step right here straight to this step right here. All of this will be able to be skipped. Okay? So what I want you to notice is a couple of things. When you take the derivative with respect to x, okay, I want you to notice that if I look at f of x cubed, which came from y cubed, this eventually became 3y squared. And if I look at y cubed to 3y squared, you can see that the power rule was used here, right? Just with the variable y instead of x. So the derivative rule didn't change. What was tagged on was just the dy dx. And the reason why the dy dx had to be tagged on was because we have to remember we're taking the derivative with respect to x of a function of x cubed. If you go over here to the right hand side, when I took d by dx, the derivative with respect to x of 3x squared f of x, the derivative of f of x just eventually became dy dx. So if you look at this here, the derivative with respect to x of y, if you just use the power rule, it would be 1, right? d by dx of y would be 1, and then multiplied by dy dx. So a number of students have asked me over the years, and they basically say this question. They say, so Ms. Yam, are you telling me that if I take the derivative with respect to x of the dependent variable y, that is not x, all I'm doing is using the regular old derivative rules, but then I just tag on a dy dx after taking the derivative of that y expression, correct? And my answer to them was yes, that is a valid way of thinking about it. So if I go through, and I go ahead here and take the derivative now, let's think about it, let's talk it through together. When I take d by dx, and the thing is I still do want you to write that you're taking the derivative with respect to x of x cubed plus y cubed equals the derivative with respect to x of 3x squared y, okay? When you take the derivative, here's what's going to happen. The derivative with respect to x of x cubed, we're taking the derivative with respect to x of that variable x being cubed. It's just the power rule, 3x squared plus the derivative with respect to x of y cubed. It's still going to be the same derivative rules, but we tack on a dy dx, okay? And the right hand side, we have the product rule. The derivative with respect to x of 3x squared is 6x times the second function untouched, y. We are not tacking on a dy dx here because we're not taking the derivative of the y expression. You understand? Okay? Plus 3x squared, now the derivative with respect to x of y, which is just 1, you put a 1 here, but then tack on the dy dx. Okay? And so that is implicit differentiation. What people often forget as you go further along is they'll often forget and say like, why do we tack on the dy dx here? Okay, and now hopefully you will understand that the reason why you tack on the dy dx when you're taking the derivative with respect to x of the dependent variable, the reason why is because in order to differentiate this and find dy dx, you have to make this implicit assumption. So doing it the long way first makes you really understand why it is that implicit differentiation works. It's because of this implicit differentiation and the resulting chain rule. That is why, okay? It would have been wrong for me just to say, boys and girls, if you were asked to take the derivative with respect of y cubed, just take the derivative as you normally would and then tack on a dy dx, okay? Because then you're just doing something without knowing why it works. So now you know why it works. And now what happens is it makes finding derivatives a little bit less arduous. So let's do this. Let's say we have this x cos y equals y squared tan x. Let's do that. Okay. And let's say here I want you to find dy dx. Okay, let's do it together, or you can pause me if you want to. But I do want you to see this. I want you to see that you write, okay, I'm taking the derivative with respect to x of the left, taking the derivative with respect to x of the right. Go ahead and pause me if you want to. I'm going to talk it through. Okay, d by dx, this requires the product rule here. D by dx of x is 1 times the second untouched cos y plus first untouched x times the derivative of cos y. It is negative sine y times dy dx equals product rule again, 2y times dy dx again because I took the derivative of the y expression times the second untouched plus y squared secant squared x. Okay, and then of course here, let me make some room. I'm not going to go to that quite yet. Let me move this down. And then when you go ahead and solve and combine like terms, what we get here is, let's see, we get cos y minus y squared secant squared x equals 2y tan x dy dx plus x sine y dy dx. Factor out a dy dx times 2y tan x plus x sine y, right? Same left-hand side. When you solve for dy dx, you will have dy dx equals cos y minus y squared secant squared x all over 2y tan x plus x sine y. Okay, so that there gives you the nice implicit differentiation shortcut. And now also you know why it is that when you're taking the derivative with respect to x of an expression involving the dependent variable, there is the dy dx tacked onto it. Okay, go ahead and find this. Okay, let's do this one. Okay, this one's going to get a little bit messy because you've got to keep track of what you're doing. All right, go ahead and try it on your own and then replay me for the answer. Okay, here's the critical step right here, actually. So again, took the derivative with respect to x of both sides of the equation. And notice here we have a chain rule. So d by dx of the cosine of xy squared. I have to deal with the chain rule. I'm taking the derivative with respect to x of cosine of Bob, right? And that derivative is negative sine Bob, right? Then I'm multiplying it by the derivative of the inner. The derivative of the inner with respect to x is going to require the product rule and implicit differentiation. So d by dx of x is 1 times y squared untouched, right? Plus x, the first untouched, times 2y dy dx. There's that dy dx. The right-hand side is dy dx. And all I did here was distributed this term to both terms here. What I'd do next is I would add this term over, factor out dy dx, and then divide to finish. Okay, the rest of it I assume, it's just algebra. Okay, but the critical step is right here, keeping it all straight. Okay, so again, now we have really nicely implicit differentiation, a nice shortcut for it. But just again, keep track of what you are taking the derivative of. If you're taking the derivative with respect to x of an expression that involves the dependent variable y, the dy dx is a tacked on factor. It's something you multiply on to the end, okay? Okay. Moving right along, what I want to derive here for you is the derivative of the natural log of x. So the question here is this, you know, if we have y equals ln x, if y equals ln natural log of x, y equals natural log of x, what is the derivative of that? This is the derivative rule we don't have. We don't have this derivative rule. And the first thing I'm going to make a note to myself is that if y equals ln x is my function, I know that my derivative function should yield positive values for all values of x, because we know that the natural log function looks like this, right? And the derivative, the slope of the line tangent to this curve, is always positive. And the derivation here, again, I just pasted the derivation from your text, but I'm going to talk you through some of it. One thing that we need to use in this proof is this limit right here. As v approaches 0, this limit approaches e, and I can't remember if I derived this for you back in the fall, like why that is the case. As v approaches 0, if you look at this here, this left-hand side, it's an indeterminate form. As v approaches 0, 1 plus v approaches 1. But 1 over v approaches infinity. So this limiting form, it's a limiting form of 1 to the positive infinity. And this is an indeterminate form. We haven't talked about this indeterminate form before. But the reason why this is indeterminate, everyone, is because if the base wins, remember our battle analogy, if the base hits 1, 1 to anything will equal 1, right? But if the exponent hits infinity before the base reaches 1, then this whole expression approaches infinity. So depending on this battle and this battle, it can have very different outcomes. This is an indeterminate limiting form that we'll work with in quite a bit in just a little while here. But this limit here, when you mess around with it, when you work with it, when you mash around, what you get is this limit actually equals e, which is incredibly surprising and satisfying at the same time and disturbing all at the same time. But let me know if I did not derive that for you in the fall. In any case, the question is, what is the derivative with respect to x of ln x? And here you have our old friend, the limit definition of the derivative of a function. Okay, and then what we have here is, look at this, the numerator has been condensed using a property of logs, specifically log a minus log b equals log of a over b. Okay, and then the argument of the log has been rewritten as 1 plus h over x, kind of a nice little algebra trick. Here, this step is very interesting. What happened here is that the variable of the limit has been changed from h to v by way of this substitution right here, and I'm going to talk about that. So note here in the little box it says they're going to do a substitution that v equals h over x. And if you let v equals h over x, notice that as h approaches 0, v also approaches 0. So notice here, h approaches 0 will also entail v approaching 0. So this equivalence, in terms of the limiting variable, is sound. The other thing is, when you let v equal h over x, 1 over h becomes 1 over vx, because h is just equal to vx. Okay? And then also, h over x is just v. Now you may wonder, what's all this for? Well, let's take a look. Look at this next step from here to here, which is really interesting. The variable of the limit is v. V is approaching 0. And if you look at this 1 over vx, right, that's the same thing as 1 over v times 1 over x, okay? And notice how the 1 over x was pulled through the limit. That's because as v approaches 0, 1 over x is just kind of standing around, right? X is not, the action of the limit is not affecting this. So whatever is happening as v approaches 0 is not going to approach the 1 over x. So that 1 over x can be factored out. And then, look at this, another property of log. 1 over v times the natural log of 1 plus v takes this property of log again. V approaches 0. And as v approaches 0, what does 1 plus v to the 1 over v approach? This approaches e. Oh, notice this too, interesting. The limit of the natural log. Remember we talked a little while ago. I remember having this conversation with you all about like the operation, the natural log operation and the limiting operation, right? The natural log is going to be taken of whatever this limit is. And we know this approaches e, and the natural log of e is equal to 1, and the result is 1 over x. So here we have our next derivative rule, everyone. We can add, we now know how to take the derivative with respect to x of the natural log of x. This equals 1 over x. Very good. And we can also now take the derivative of, let's say, log base 3 of x, because the natural question you have is, what if you want the derivative of log base 3 of x, not of log base e of x? Well, I'm going to use our very handy-dandy change of base formula. Log base 3 of x is no more than the natural log of x divided by the natural log of 3. Remember, log base 3 of x, I can write it as a quotient, log of any base of the argument divided by log of any base over 3. I just happen to choose the base of 3. And 1 over ln 3 is just a number, it's a constant, times ln x, right? So the question is, what is dy dx, where y equals, right, 1 over ln 3 times ln x? Well, guess what it is? Dy dx will just be the constant, 1 over ln 3, times the derivative of ln x, which is 1 over x. And you'll usually see this as 1 over x ln 3. So another derivative rule that we just derived here is this. The derivative with respect to x of any log base b of x will always just equal 1 over x ln b. Add this to our derivative rules. We now have the derivative of logarithmic functions. And of course, you know, once we open a new can of worms, a lot of things become available to us. Like, let's take a look at this one. Let's say I've got something like this. Y equals sine squared of the natural log of x cubed plus 2x squared. Might as well go out with a bang, right? So it's if y equals that, tell me what dy dx equals. Okay, maybe the first thing I'll do here is rewrite this as y equals, just so it's extremely explicit to me what the outermost function is. It's all of this being squared, right? And you see that y is a composition of, here's the innermost function, x cubed plus 2x squared, then it's the natural log of that, then it's the sine of that, then it's all of this squared. So y equals Bob squared. So here I go. I'm going to go right into finding dy dx. Equals 2 Bob to the first. I'm going to fill in Bob. Sine of natural log of x cubed plus 2x squared times the derivative of the next innermost function, sine of Bob. It's going to be cosine of natural log of x cubed plus 2x squared times the derivative of the next innermost, which is, oh dear, what just happened? Oh no. Okay, derivative of natural log of Bob is 1 over x cubed plus 2x squared times, finally, derivative of the innermost, 3x squared plus 4x. And we are going to leave it long and disgusting because there's nothing else we need to do with it. All right, and okay, so this is the homework that relates to this screencast. And what I'm going to do, the highlighted questions here, these highlighted ones, I'm going to do the solutions for those below so you can check. And the reason why I'm doing that is because I know it's going to be quite a while until I see you again. And these 4 are probably the more challenging of the problems in this problem set. And so I'll work those out probably in a separate screencast, okay? That way you can kind of check your work and not have to wait to address any questions on these 4 until after spring break. And like I said, I will post the rest of the spring break homework by the end of the day tomorrow. Have a wonderful spring break, everyone.